So I'm willing to talk about the processes once again. Sorry if I tired you at the first time, but now I'll talk about as it was in the question, about the sequence model and how we applied it to the task of event log analysis of .NET. The agenda of my talk will be the following. We'll talk about the domain and the objective of the three algorithms that we use and make some results in the end. So what is the .NET? .NET is an environment that supports the development and execution of component-based application. It can be used for desktop application, web, mobile, gaming application like Unity framework, and so on and so forth. And in this project, we considered the .NET Core with the version number 6. And what is the CLR in the .NET? CLR, or Common Language Runtime, is a key subsystem of .NET which manages program execution. What's going on when you create some program using .NET Framework? You write the high-level code using some .NET programming language like C#, F#, and then compile it. When it's compiled, it is compiled to the pseudocode called CIL, or Common Intermediate Language, and the CIL defines a set of commands the set of instructions that are independent of a particular architecture. So they are independent on the operation system that your machine is using. And then the purpose of the CLR is to convert these high-level instructions of CIL code or byte code to the native machine code that is applicable to this architecture and to this operational system. So CLR converts byte code to the native machine code. And once again, we used process mining techniques to analyze the events that appear during this byte code to machine code conversion. We already know these basic concepts like activities and events. And in this project, we consider events, like I said, that appear during the conversion process from byte code to the native code. The activities presented in such processes can be viewed at the different levels of abstraction. For example, take an activity GS, sampled object allocation of the system byte. Here, GS stands for garbage collector, and the garbage collector allocated some array of the bytes, and such activity presents the most specific level of abstraction. It can be considered as allocation of any object type, like GS sample object allocation, and such approach of increasing the level of abstraction of the event is applicable to all other activities in the business process. So in our project, we considered 154 unique standard-defined activities that can appear in .NET CLR environment. And as I said, we already talked about the trace and event log concept. So once again, the trace is the sequence of event that appears some process. And here, by process, we mean the program execution. When we execute some program, the process of CLR environment starts, and it creates some log for us, and we take traces out of them. So one trace stands for one execution of a process of a program. When we execute it several times, we get several traces, and the combination of these several traces create an event log. And so the objective of our research is to create a method with a sequence model, like NLP approach, some NLP approach, talking more formally, to analyze .NET CLR events in two cases. The first one is also the finding of patterns. And the idea of finding patterns is really spread in the process mining discipline. And the other task is to find anomalies in process execution, which is really important when we talk about the software. Finding anomalies in this execution will help to enhance the software itself and make it more stable and efficient. So finding anomalies in here in it is really important. And the first algorithm that important for us is tokenization. I guess everyone here understands what it is. So simply, tokenization is just splitting the sequence into smaller subsequences, and such small subsequences are called tokens. It can be for simple text like this is tokenizing. It can be done on the character level, word level, or subword level like this. And what is important with the tokenization for us is that we want to tokenize such traces so that it can be later analyzed by some NLP model. And when tokenizing such traces, we want to consider the smallest indivisible unit an event. So in event is the most indivisible unit, like character here or word here. We cannot divide this thing anymore. We have to convert, or you may say encode, our traces as simple sequences to which we can tokenization algorithms. So to do so, we create a set of activities. Like I said, we can 154 standard defined activities of CLR environment, and we create some subset of non-control Unicode characters. And then we can define a simple bijection between these two sets. For example, if we have some activities like this, method, garbage collector, and buffer, and we have some Unicode characters like ABC, then such trace of these activities can be simply converted to the trace of also activities but encoded like symbols ABC, and then such symbols can be treated like a simple sequence of characters. A similar approach is applied to each trace in our dataset, and as a result, we have a dataset of simple sequences that can be processed by standard tokenization algorithms. And among the tokenization algorithms, we selected probably the most common which is BPE, or byte-wise encoding algorithm for tokenization. And if you don't know how it works, it's quite simple. And how we use it, let's consider, for example, a subset of set A consisting of 10 events, and how we encode them with Unicode characters. And if we have following traces of events in our dataset, we can encode them to such sequences. And tokenizer, the model that makes tokenization, is a trainable model, trainable element of a system. And when we train it, with the help of training dataset, we simply add a pair of tokens that most frequently occur in a training dataset. We treat such pair of tokens as a new token, token alpha, added to the base dictionary, and then in a training dataset we find a new pair of tokens that appear. This process goes till it reaches stopping criteria that can be the vocabulary size or the maximum token length, and so on. Also, one important thing of tokenization result is the following, that when we traces of process program execution can be really long. For example, 25,000 events in a trace. But when we use tokenization, it can shorten really significantly. And this is important for us because we use a sequence-based model, and this model has a short context, and we would not be simply allowed to analyze such big traces, such big sequences, but with the tokenization, they are shortened really significantly and can be analyzed by our model. So the whole pipeline of traces encoding is presented here. When we have a trace, we encode it with some simple characters of Unicode, then we tokenize them, and for every token, there is an vector embedding for it in some embedding table, and these embeddings are trainable parameters of the system too. And this is some simple pseudocode of tokenization algorithm. And going on to the patterns, what we define by pattern in this project, a pattern here is simply a repeating sequence of events in a trace that frequently appear together. Like when in a process, some events like garbage collector, then method allocation memory, and once again, garbage collected appear together. These three events together, we consider them as a pattern. And based on this, we can say that the set of trace patterns is simply the trace tokens of the trace tokens. And there is some statements that mean that if we can tokenize our trace and decode it as a sequence, we can vice versa, based on the tokens, get the events of a trace. So pattern detection was performed across 13 levels of abstractions, and for each level of abstraction, there is a special tokenizer assigned for it with the special hyperparameters like vocabulary size limitation or maximum token length limitation. And let's see the results and the examples of pattern detection algorithm, how it works on such program, such simple C# program. When we execute it 25 times, we get the following result. In this image, 25 runs of the program are shown. On the x-axis, there is the length of the trace, the length of elements on the sequence, and every color on this image is responsible for event. So one color defines one, one color defines one activity. So different colors, different activities in a trace. And this, how it looks without any tokenization algorithms applied. We can see some patterns in such image already, like in this and this side, but still these sequences are really long, and we can apply tokenization for them with tokenization level of abstraction 2. Result that traces become 1,000 elements, but around 1,000. And we can already see that this and this trace differ from the others, and we can examine it further with some classical process mining approach. We shortened the amount of different combination of patterns, and so with the help of our algorithm, the pattern detection algorithm, we can obtain new activities and make some process models and examine them later. So this is basically all for the pattern detection algorithm. And going to the anomaly detection, the problem with this task is that there is always an imbalance between the number of anomalies and normal execution examples. And also, if we even have some examples of anomalous behavior, we only limited to the known cases. And this leads us to the need to treat anomaly detection task as a self-supervised learning task. And for this task, we used an attention algorithm and the transformer architecture built upon it. And the key concept of attention and the key concept of transformer as a self-attention algorithm that is, I guess, well known in the audience. So primitively, the goal of self-attention algorithm is just simply to multiply the value matrix to some certain weights that are calculated like shown in this slide. And in our work, we use a model based on the BERT architecture that uses only the encoder part of the transformer, but not the simple BERT, but the architecture called SqueezeBERT. This is the optimized version of the BERT when optimized in the fully connected layers that are replaced with the convolution. And this, the authors of this work demonstrate that this approach allows to the more efficient execution of a model. How we train the model? We used the technique called mask language modeling, when we mask certain tokens of our sequence. And the task of the model is to predict what element of the sequence was masked based on the surrounding context. And the most important thing for us here is that when we trained our SqueezeBERT model, we used only normal program execution where no anomalies are presented. And by doing so, we believe that BERT model is able to understand the normal behaviors that are presented in the program execution processes. Here I show that we used the LAMP optimizer, the original optimizer presented in the SqueezeBERT paper, and compared to the ADAM-V, one of the most popular optimizers nowadays, LAMP optimizer works better. And there is some statistics for the model training. Yeah. So how we detect anomalies? We use three metrics to say that the trace anomalous or not. And there are three metrics: the probability, loss function, and the Breer score. And if any two of these metrics exceeds their threshold values, we say that in this situation, the trace is classified as anomalous. How anomaly detection algorithm works? On example, if we have some sequences of tokens, what we do? We mask every token in the sequence and ask the model to predict what token should be on this position based on this context. And remembering that our model was trained only on the normal programs with a normal behavior, we believe that model should say that what token should be presented here in a normal situation. And if the prediction of a model is not aligned with the tokens that are really placed in this position, then we say that this token is anomalous, because the BERT model knows what should be there in a normal situation, and if this is not the case, if there is something another in this position, then this is the anomaly. We can also consider anomalies in a grouped levels when a group of tokens anomalous and should not be presented in a sequence. And we do so by masking randomly select group of tokens in a sequence which tokens should be there, and then using such formula, we calculate the Breer score. And if this exceeds the threshold, we say that such trace is validation results are the following. We created 25 synthetically generated anomalous traces and 25 normal traces of program execution. And this led to the following results. Model is able to detect, was able to detect all anomalies and made just a few mistakes when saying that normal trace is considered anomalous. But the important thing here is that this approach is not really generalizable, because if we when we tested our model on a different domain of the programs, let's say we had the program from one system, banking system, and if we take healthcare, another software system, this most likely won't find any anomalies in such system. This can be the result of the lack of the data that we had, and probably the lack of the resources to train the model. But we think that it can be that we can overcome this by gathering more data and conducting more and more experiments on the model architecture. I also created some simple command line tool for using this model and using algorithms for pattern detection and anomalies detection, and presented it in the same simple demo. And the results of the project is the tool that I've shown to you is available on GitHub, and the model that is available on Hugging Face. So that's it for it. Thanks.
Thank you. Thank you, Maxim. Yeah, we have questions, please.
Thank you for your speech. I have two questions. First question related to data that you use to train your model. So as I understand, for such a task, to have data, you need logs for like thousands of different programs that have run maybe on different platforms. Of course, common media, this CLR, but anyway, maybe on a different hardware. So how you solve this task to collect that data?
So, thank you for your question. You understand it right. We gathered some open source projects and executed them by ourselves. And this way we got the process logs. And also we have just simply handwritten some programs by ourselves and also executed them. And by this way we gathered some process execution examples like this.
Thank you. My second question is related to real-life application of your analysis and maybe some software. So as a developer, I understand that if I have some tool that tells me that there is anomaly in my application, it's not very useful on its own. So the next step is naturally that it tells me in natural language some particular problem, like you have memory leak. I think you have memory leak here, or you have some undefined behavior maybe. So how do you have plans to improve your approach, to have additional training or additional models to use to detect not just anomalies, but also some system to signalize what particular anomalies are there?
Yeah, great question. Thanks. Yeah, there are some ideas to embed our approach to the IDE system, probably the rider system for creation of .NET application, and how we can say that we have some, like you said, memory leak. I've shown this on this slide here. When we when we have when we decide that some token is anomalous, probably better shown here. Like we say that this token is anomalous, we understand which activities create this token, how this token was done by which combination of activities, and based on the activities we can say what anomalous behavior we have seen, like this. But yeah, there are some improvements that should be done to say it more precisely what should be corrected in the system, and yeah, there is still work to do.
So at this slide, as I understand, you just train model to predict missing token that you've masked, but you don't have a label like this is this particular problem.
If we say that token is anomalous, we I guess we understand that the anomaly is presented in the is the result of the activities presented in a trace. So if the anomaly is on this token 1, and token 1 is the combination of activities like method memory allocation and garbage collector, and this can be easily done like this. If we combine these activities to new token, add it to vocabulary, and they then say that token alpha is anomalous, then we can say that if the token alpha is anomalous, this is because of the presence of these activities, and these activities are some memory allocation, like this.
See, thank you.
Thank you. Do we have other questions? Yes, please.
Thank you for your speech again. And could you tell us, is recall more important or precision more important in evaluating this task? And maybe you should use F-score with different parameter, maybe if recall is more important.
So for the metrics, I think that the more important thing is, let's move it to them. Yeah, that probably the more important thing for us is to detect all the anomalies in the trace. So recall is more important for us, because if we detect if we say that some normal trace is anomalous, we can perform some more analysis and say that, yeah, this probably was a mistake of a model, and anomalous trace is actually normal, so no need to do anything else. But if we miss some anomal trace, if the model says that it's normal, but that's not the truth, that is the worst situation. So here is recall is yeah, more important.
And maybe you can use not F1 score, but F score with different bit parameter. Okay, thank you.